moving into section 7. We just talked about all of these graphs of our basic functions, so now we are getting into the transformations of our functions. You did transformations last year in Algebra 2, but you only did them on parabolas and absolute values. So now we are extending it to all of them. We're also going to add in a couple that we glossed over in Algebra 2 because we were nicer then, and now we're not nice anymore. So, first thing that we're going to add in is vertical and horizontal stretching and shrinking. This is the piece that we kind of glossed over last year, and we only did really, really nice versions of. So I put on your handout the definition. Basically, what it's saying is if you have a number out in front of your function, so a times f of x, if I am multiplying by a number, that will either vertically stretch or shrink your graph. Okay, what I always tell people is anything on the outside is going to change y, and it does what you think. So if you multiply by a number bigger than 1, it's like going to stretch your graph. It's going to take all your y's times that number. If the number is smaller than 1, it's going to shrink your graph. It's just like multiplying y by that number. Horizontal. This is the tricky one. Anything on the inside changes your x, and it does the opposite of what you think. So, if I have a number multiplied with my x, if that number is bigger than 1, it is actually going to shrink my graph horizontally. If that number is smaller than 1, it is actually going to stretch it horizontally. So inside, when it's changing x, it does the opposite of what you think. The best way to make sense of this is to look at a couple examples and talk about how we would get these transformations. So let's start out with the vertical ones, the nice ones. My expectation is, anytime I'm asking you to graph transformations, I want the parent function as a dashed line. So the parent function would be all those functions we covered in the last section. And then I want the final function as a solid line. I want a minimum of 3 exact points on each of those curves. So, if g of x is 2x cubed, what would my parent function be? X to the third. Okay, so we need a minimum of 3 exact points. So 0 to the third is 1 to the third, negative 1 to the third. Okay. You could do more points if you wanted. You could do 2, 8, 2, negative 8. As long as you realize that this is x cubed, it's a chair, this is sufficient. So minimum of my 3 points, dashed line because that's my parent. Now, this 2, it's outside my function. So that is a vertical change. Y's do what you think, so this is a vertical stretch. Okay, if you struggle with this, we could think about the ordered pairs on my graph right now. Those are the 3 points we just plotted, right? This 2 would be like multiplying each of these y's times 2. So the 0.11 would become the 0.12. You multiply the y times 2. The 0.00, if you multiply your y times 2, it's still 0, 0. 1, negative 1, if I take my y times 2, it's negative 1, negative 2. Okay. It's just like if you take a rubber band, the more you stretch it, the skinnier it gets. That's what's happening. I'm vertically stretching it, so it's getting skinnier as it goes up. Are there questions on that? So let's look at the 1/2 x cubed. It's the same parent function. You could even draw them on the same graph if you wanted to label which was which. I'm going to do a separate one. So we still have the same 3 original points. If there is a 1/2 out in front, what will that do to my graph? A vertical shrink. Anything on the outside changes y, it does what you think. So it is just going to multiply each of my y values times a half. So 1, 1 would become 1, 1 half. 0, 0 would become 0, 0. Negative 1, negative 1 would become negative 1 half. So I see my vertical shrink. If you take it and you're mashing it down, it's getting fatter, shorter and fatter. So vertical, anything on the outside, changes y and it does what you think. Take your y times half, take your y times 2. Are those examples okay? Get back to the next one. I want to sketch y equals f of 3x and y equals f of 1/3 x, when f of x is the square root of x. In other words, I'm graphing f of 3x would be when you plug a 3x in for your x. So I'm going to graph the square root of 3x and the square root of 1/3 x. Those are the two things we need to graph. All right. This is on the inside. Inside changes x, and it does the opposite of what you think. So multiplying by 3 will actually be a horizontal shrink on my graph. Let's graph our parent function. Parent function was the square root of x. Square root of 0 is square root of 1. Do we want to do a square root of 2? Probably not. What would be another good number? Square root of 4 would be 2. So I'm just kind of making that t-chart in my head. That's my parent function. So let's talk about this one. If you took those points, you wrote those out. This 3, inside changes x, but it's the opposite. So instead of taking my x's times 3, the opposite of multiplying by 3 would be divide. So it would be like dividing each of these x's by 3. So 0 divided by 3 is still 0. So 0, 0 doesn't move. 1 divided by 3 would be 1/3 1. 4 divided by 3 would be 4/3 2. So what we see is when we horizontally shrink this, if you take it and mash it in, it's going to make it get taller. Okay, so we just took this and we compressed it this way. So our graph got shorter and taller. Inside this x does the opposite. We divided our x by 3. So let's talk about this 1/3 x. It's on the inside, so it's changing x. The 1/3 would be a horizontal what? Stretch. So if you think about it, if we're going to take our graph and stretch it out horizontally, what should happen to it? It's going to get shorter and longer, right? If you take your points, so the points on my parent function, this time instead of taking my x's times 1/3, it'd be like dividing your x's by 1/3, which is the same as multiplying by 3. you are taking your x's times 3. So 0, 0 doesn't move. 1, 1, if you take 1 times 3, you get 3, 1. 4, 2 would become 12, 2. So we see our graph went like that. It got really short and stretched out horizontally. So the writing out ordered pairs piece is not something I would grade, not something I would necessarily take off points if you didn't do, but for the stretching and shrinking, it can be very helpful for you if you write out those points and think about, okay, am I changing X or Y? What am I doing to it? And that'll help you prevent mistakes. Okay, so far so good? Let's do a couple more. So what is my parent function on the first one? X squared, parabola. So at least 3 points, 0 squared is 0, 1 squared is 1, negative 1, 1. If you needed more, you could do like 2, 4, negative 2, 4. So that's our dashed one. What is that 1/3 going to do? Is it horizontal or vertical? It's vertical. You're going to square it first and then multiply it by 1/3. So it's a vertical. Vertical does what you think, so since it's smaller than 1, it will be a vertical shrink. So all that's going to do is take our y values times 1/3. So this is a y value of 0, 0 times a third is still 0. This is a y value of 1, 1 times a third is 1/3. This is a y value of 4, 4 times a third is 4/3. Same thing over here. You can write them out if you need to, you can just kind of talk through them like I did. But we see that vertical shrink is making our parabola get fatter. B, we have the same parent function. But what's happening on this one? Is that horizontal or vertical? Horizontal. It's inside. Horizontal means you're changing your x value first. You know, so if order operations, if that would be the first thing you would do, it's on the inside, it's attached to your x, it's a horizontal. Horizontal does the opposite of what we think, so this would be a horizontal shrink. So horizontal changes your x, does what you think, so this isn't, or does the opposite of what you think, so this is an x of 0. We would have to divide our x's by 4. 0 divided by 4 is still 0. This point has an x value of 1. 1 divided by 4 is 1/4. This has an x value of 2. 2 divided by 4 is 1/2. Here you're at negative 1. Negative 1 divided by 4 is negative 1/4. Negative 2 divided by 4 is negative 1/2. So that horizontal shrink just matched our graph in. Alright, questions on this? I've got a couple more on here. Do we need to practice some more? Give them a shot. Try it. Parent function and transformation. So C is the absolute value. What's my transformation here? What's this going to do? Horizontal or vertical? Horizontal. Okay, that's smaller than 1, so that would make me think shrink, but I know horizontal does the opposite, so it is a horizontal stretch. So think about it, if you're going to take it and stretch it out across the x-axis, it should be getting wider and flatter, right? So we do this by changing our x's. Instead of multiplying our x's by 0.25, what are we going to do to them? Divide them by 0.25, which is the same as multiplying by 4. So 0 times 4 is still 0. This is the next value of 1. 1 times 4 is 4. Okay, over here, negative 1 times 4 is negative 4. So we get this. Oh, I can't draw a straight line for our absolute value. This one, we didn't do x to the 4th as a parent function, but we could still get it, couldn't we? 0 to the 4th is 0. 1 to the 4th is 1. Do you want to do 2 to the 4th? No. That turns into 16. Let's not. Negative 1 to the 4th is 1. Negative 2 to the 4th would be 16. It's just a skinnier parabola. Okay, what's that 5 going to do? Vertical stretch. So it's just like taking each of your y's times 5. So 0 times 5 doesn't go anywhere. This is the y value of 1 times 5 is 5. Y value of 1 times 5 is 5. So we get this skinnier parabola. Alright. Are we okay with that stuff? It's probably the hardest thing I'm going to do with you today, because the rest of it is more like what you did in Algebra 2. Okay? The next few transformations we're going to talk about reflecting and moving up, down, left, and right. If it's on the outside, it's changing your y. So negative on the outside would mean making all your y's negative, which actually flips it over the x-axis. A negative on the inside makes your x's negative, which would flip it over the y-axis. If you add and subtract on the end, that's y, so it does what you think. Adding moves up, subtracting moves down. If you add and subtract on the inside, subtracting actually moves you to the right in the positive direction, adding moves you to the left in the negative direction. Okay, so let's just try a few. We may or may not do all the ones I have on here. We just kind of need to see how we're doing and go from there. So my parent function would be x squared, 0 squared is 0, 1, 1, 2, 4, negative 2, 4, negative 1, 1. So at least 3 points. Dashed line. What's that negative going to do? Flip over. It's on the outside, so it's like taking the y values and making them negative. So it flips it over the x-axis. So 0, 0 won't move, but the other points will come down. So it becomes 1, negative 1, 2, negative 4, negative 1, negative 1, negative 2, negative 4. Second one, what's my parent function? 0, 0, 1, 1. What would be another good 2. You could do 9, 3 if you wanted. It's just our square root. Okay? Negative on the inside. It's making your x's negative, so it flips it over y-axis. So just think on each of these points, if you make your x negative, 0, 0 doesn't move. This goes to -1, 1, -4, 2, -9, 3. So we get that. Do we need more of the reflecting examples? I'm going to skip the next slide then. I'm going to go to this one. So the first one, x cubed plus 4, what would this do? Up 4. So x cubed is, what does it look like? The chair, 0 cubed is 0, 1 cubed is 1, 2 cubed is 8, -1, -1, -2, -8. Does everybody know where I get the points from everything? So now we just have to take each of those points we plotted and move them up 4. I'm going to change the, let's do it like this. Let's do the absolute value of x minus 2. Let's switch the problem up. What's the absolute value? The absolute value is 0, 0, 1, 1, 2, 2, -1, 1, -2, 2. So my modified problem, what's this going to do to the graph? So inside does the opposite, so we're actually moving it in the positive direction. So each of those points gets moved right. I've tried to put lots of examples on here. The next slide just has 4 more examples of the moving left and right, up and down. Do we need those? We'll skip it for now, but let's do some that combine multiple transformations. So we're not moving on yet. We're just going to go to some that have multiple steps. This one, I gave you a hint. The very first thing I would do on this problem is factor it. What could you pull out of 2x minus 4? We could leave it like this. We could even, do we know what the absolute value of 2 is? 2. So could I pull it outside my absolute value? Should be a 2 right there. I'm going to go ahead and pull it out because I prefer to work with vertical transformations anyway. So you could have left it inside and thought about your transformations like that. But written like this, it's even a little more obvious what's going to happen. What would this 2 do? Vertical stretch. In other words, we're going to take our y's times 2. What's this do? Right? 2. Right, so the parent function is the absolute value. 0, 0, 1, 1, 2, 2, negative 1, 1, negative 2, 2. Vertical stretch says I'm going to take the y value times 2, and then we're going to move it right 2. So if you're at 0, 0 times 2 is still 0, and then go right 2. This has a y value of 1. 1 times 2 would be 2, and then we move right 2. Okay, if you look at the point 2, 2, it has a y value of 2. 2 times 2 is 4, and then right 2. Okay, see how I'm getting these? If you need to, write out your points. Now I'm getting ready to do the negatives. I'm taking my point, I'm taking the y times 2, so this becomes negative 1, 2, and then we have to move it to the right 2. So negative 2, 2. If you take your y times 2, that's negative 2, 4, and then I move it right 2. So that would be my final part. How much of this do you guys remember? We can do 1 or 2 more. Go ahead and do this next one. What will that 1/2 do? Vertical shrink. What will the plus 2 do? Left 2. What will this minus 3 on the end do? Down 3. Okay, parent function is the square root. Square root of 0 is 0. 1, 1, 4, 2, 9, 3. If it helps you, you can write out your points. Not required, but it can't hurt anything. The first thing you need to do is this vertical shrink. Vertical changes y and it does what we think. So if I multiply by my y by 1/2, that one doesn't go anywhere. Then I move the point left and down. So 1, 1. If you multiply your y times 1/2, you get 1, 1/2. So you're here. Then you go left 2, down 3. Or 2. If you take your y times 1/2, that gives you 4, 1. Then you go left and down. There's my 3, but I could do another one if I wanted. 9, 3. If you take your y times 1/2, you get 9, 3/2, or 1.5. Then you go left 2, down 3. So that's our final. Where are we at? I'm going to do this one, except there's a typo. That cube should be on the outside there. Try that. What's the negative on the outside do? Flip it over the x-axis. What's the minus 2 do? And the plus 1? Up 1. You do need to make sure that you flip before you move up and down on these. So 0, 0, if I flip, doesn't go anywhere. Then write 2 up 1. 1, 1, if I flip, it moves down here. Then write 2 up 1. If you went to 2, 8 and you flip, it goes to 2, negative 8. Write 2 up 1. Negative 1, 1, if you flip it, it goes up here. Write 2 up 1. Negative 2, negative 8 would go to negative 2, positive 8. Write 2 up 1. Should look something like that. We're going to talk about a few more things. The next slide, we have to use transformations, but I didn't tell you what the parent function was. I gave you a picture of the parent function. So we have to be able to look at that graph and move it. I might put these questions on the test just to make sure you can do it without a graphing calculator, because you don't have a function to plug into your graphing calculator, so you have no way to check your work on these. So on this one, what would that minus 2 be to my graph? Down 2. So here is my function. Just find yourself some nice points on there, and you are going to move each of those points down 2. What's the second one do? Right here. So again, just take nice points on the graph. Move each of them to the right. See. What's this one doing? Up 1 and up 2. Take your points. Each go left and up. Okay, D is probably the hardest. What's this going to do? Flip over the x-axis, then right 2 and up 3. So you have have to flip first. So if I take this first point, -4, 0, and I flip it, it doesn't go anywhere. Then write 2 and up 3. If I take the point at -2, 2, and flip it, it's at -2, -2. Then write 2 up 3. Okay, if I take 1, -2.5, and flip it, it goes up to +2.5. Write 2 up 3. Should I only go up 2 on that? It would be a +2.5. Right, 2 up 3. Right. And then if I take 3, 2, flip it, it goes down to -2. Right, 2 and up 3. So that's our final graph. Okay, so same concept, you just didn't have a parent function that you could have graphed on your calculator. You had to think about it on by hand. Any questions there? Alright, the last things I want to talk about are symmetry. We'll see how much of this we get through. It'll go pretty quickly. I'm going to kind of jump around on here. There are 3 types of symmetry. I'm going to go ahead and talk about all 3 types before we do any examples. If a graph is symmetric to the y-axis, what that means is that if you folded your graph on the y-axis, those pieces would overlap each other. So in other words, both a positive x and a negative x give you the same y value back. If it is symmetric to the x-axis, that means if I fold my graph on the x-axis, it would overlap itself. So in other words, both a positive y and a negative y correspond to the same x value. If it's symmetric to the x-axis, can it be a function? The third type of symmetry is symmetric to the origin. That means you would have to flip over both the x and the y-axis before it would overlap itself. So if you have a point like 1, 1, you would also have -1, -1. You have to change the sign on both the x and the y to make it work. So we can test for symmetry a couple different ways. You can look at a graph and tell from the graph. However, our graphing calculators can only do things if it's y equals. So if it's, like the absolute value of y equals, we can't necessarily do it. The algebraic way is to do this. Plug in negatives for our variables and see what happens. So we're going to talk about both ways here. I'm going to kind of pick and choose my examples and we'll look at a few. So I'm just going to figure out what kind of symmetry this one has. So you could I graph this one on the graphing calculator and look at it? No. To check for symmetry to the x-axis, that means if I fold it on the x-axis, it overlaps itself. If you read the definition I told you, if you put in a positive y or a negative y, you get the same thing back. So what we'll do is just plug in a negative for the y. Now what happens if you do the absolute value of negative y? So did I get the same thing back? So this one is symmetric to the x-axis. To check symmetry to the y-axis, you make your x negative. If I make my x negative, is there any way to get rid of that? No. So is it the same as the original? No. So this one is not symmetric to the y-axis. To check the origin, you do both the x and the y. there's nothing I can do about it. The absolute value of negative y is the same as the absolute value of positive y. But did this turn back to the original? No. So this graph is symmetric to the x-axis. Let's do D. How do I check symmetry to the x-axis? Change y to a negative. If you take a negative and square it, it becomes positive. Is that the same as we started? So this one is symmetric to the x. How do you check the y? Make your x negative. If you make your x negative and square it, you get a positive, which is what I started with, so this is also symmetric to the y-axis. How do we do origin? Both of them. The x gets a negative, and the y gets a negative. But squaring a negative gives us a positive, and so that one is also a yes. In general, you can get all three to be no. You can get one to be yes and two to be no, or all three will be yes. You'll never have two yeses and one no. Okay. Really all we have left to talk about is even and odd functions. So I will take probably the first 5-ish minutes of class on Monday to finish it. If you would like to start the homework between now and then, you are welcome to do so. It is on the very last slide.